These are the 7.2 notes, and we're going to continue looking at sample proportions here. Now, a lot of sampling distributions we can actually end up making normal depending on the conditions, and we're going to kind of break this down. So in many of the cases, our sampling distributions appear to be a normal distribution, and I think that you've kind of started seeing this as we do our sample distributions. We have like a high center around what the population proportion is, and then that tends to be where our center is, and then we have an approximately symmetrical graph from there. So we kind of have this approximately normal looking graph. Now it might not be perfectly normal every single time, but as we do more and more samples, we tend to kind of see these approximately normal size. In these normal distributions, the average of the distribution proportion is equal to the proportion of the population. So what we say here is this is the average of the sample proportion. So this is as we are going through and we are taking many samples. We have like 30, 40, 50, 100, 200 sample proportions. If we take the average of all of those sample proportions, it will be equal to the proportion of the population, which is the exact same thing as saying it's an unbiased estimator. So if we have this unbiased estimator, if we have the mean of our sampling distribution equal to the proportion of the variable we are looking at in the population, then we are said to have this unbiased estimator. And so we're assuming in these normal distributions that our sampling distribution mean, the mean of our sample proportions, as we take all those proportions, average them out, and figure out what is our average proportion, it should be equal to the proportion of the population. It should be an unbiased estimator. And this is the center of the normal distributions. This is the average for those normal distributions we're going to use. The standard deviation is going to depend on the size of the sample. And again, we looked at this in the previous chapter. As we saw, when the sample gets larger, that variability gets smaller. If I have a proportion at like 50% and I want to figure out what's going on in the population and I'm taking a sample size of 25, I'm going to get a lot more variability than when I get a sample size of 50. The larger and larger of a sample size I get, the closer and closer those samples tend to get to that true mean value, that actual average value. So if I'm taking sample sizes of 30 versus sample sizes of 100 versus of 1,000, each and every time I move up the number of my sample size, I should be theoretically getting closer and closer to that true average with each sample because I'm taking away a lot of that variability. Those kind of extremes that I might pick up in a sample size of 20 will be balanced out more in a sample size of 300 by a higher probability of picking up the other extremes. So those mean values don't get changed as much, and because of that, the larger sample you have, the smaller your standard deviation is. Now, we can think about these as a binomial approach with our sampling distributions here. And this leads into what we were looking at in Chapter 6. So with a sampling distribution, when we think about if we're taking a sample of the U.S. population, or I'm a quality control person at a company and I'm taking a sample of the product that we're sending out, if my sample size is less than 1/10 of the entire population, I can think about it as a binomial. I'm thinking about it as each one of these is the exact same percent chance of success or failure. Yes, as we find people who are successful, it should theoretically limit it, but it's such a small difference when we're talking about really large populations and small sample sizes. So like, for example, when we're taking unemployment data in the United States and we're sampling 60,000 people in the United States, that's a pretty big number, but it's also much smaller than 10% of the population. And since it's a lot smaller than 10% of the population, I can basically say, all right, this is going to be a binomial distribution. You're either employed or you're not. You have a success or a failure. There's going to be a percentage chance that you're unemployed or you're not employed. That's kind of what we're getting from the data. We're trying to extrapolate that to the proportion size, but there's going to be a percentage chance that you're unemployed, a percentage chance that you're employed. We're going to have that set number, the 60,000 that we're sampling, and then each of those is going to be independent. Every single person, and I get, again, like when we're talking about unemployment, things like that, you might be able to argue, well, if one person has a job, another person can't occupy that job, but we're still considering it independent. We're considering everyone is employable to some degree. Everyone should theoretically be able to find a job if the jobs are available, so on and so forth, and that's how we are able to kind of figure out what is the unemployment rate there, and we're able to use that binomial distribution to approach it. So that's when we have these very, very large populations and our sample size is a tenth the size. And then if we remember from binomial distributions, we have the large counts condition. The large counts condition is if the sample normal, and this allows us to consider the distribution of the sample to be normal if the size of our sample, n, so this n here is size of sample, times the proportion, and size of sample times 1 minus the proportion are greater than 10, then we can say that the large counts condition is met. And since that large counts condition is met, we can say that this is an approximately normal distribution. So we're like, this all kind of goes together. When we have these really, really large sample sizes that allow us to get this. So again, like if I have a sample size of 10, I can't consider this normal because a sample size of 10 will never meet this large counts condition. N times anything less than 1 is going to be less than 10. So like I need to be getting sample sizes of like usually a minimum of 20, and that's only if you have 0.5 and 0.5. You're going to be looking at sample sizes here usually of like 50 to 100 at a minimum. And then when we get to larger populations, 1,000, 2,000, that's when we can start considering these samples normal distributions and we can start thinking about the probability of these occurring. So this leads us to all of these rules, and this is just a bunch of formulas, and this is kind of based on everything here. So the mean of the sampling distribution is the proportion of the population. We already saw that in the first slide. We're just assuming that if the proportion population is this is going to be an unbiased estimator. The standard deviation is based on sampling size, so again, this n is size of sample. And this should look just a lot like that binomial distribution. So this is, we're basing the size of our standard deviation based on standard deviation with those binomial conditions that we learned in chapter 6. This is the same standard deviation formula. It's based on that standard deviation formula from binomial conditions. And then we're looking at our sample size. So the standard deviation of a sampling distribution is going to be based on the square root of the proportion times 1 minus the proportion over the size of the sample. And this only is as long as we're at the 10% condition. And we have to make sure that we have that approximately normal because we're meeting our large counts condition with that binomial distribution. So we're going to do a brief check for understanding. There's a little bit more to this where you might start applying z-scores, but once we have the idea of what is the standard deviation, what is the z-score, we can move from there. And I'll touch on that a little bit at the end of this check for understanding. So we're going to say about 75% of young adult internet users ages 18 to 29 watch online videos. Suppose that a sample survey conducts a simple random sample of 1,000 young adult internet users and calculates the proportion in the sample who watch online videos. What is the mean of the sampling distribution? P hat, explain. Well, the mean of the sampling distribution is equal to our proportion of the population here. We're going to assume that the mean of the sample distribution is going to be an unbiased estimator. And since we're making that assumption, that means that it's just going to be equal to 0.75. We are working purely under the unbiased estimator assumption at this point. Now find the standard deviation of the sampling distribution. Check that the 10% condition is met. The first thing I'm going to do is check the 10% condition. So we've got 1,000 young adults, and this is, it says internet users. We don't have a number of young adult internet users, but I think we can all agree that it's above 10,000. So as long as we have 10,000 or more young adult internet users across the country, world, whatever we're considering here, we are looking at meeting the 10% condition, which I think we've easily met with 1,000. We don't know the total number, but I think we can definitively say 1,000 young adults is well below 10% of the total number of internet users, of young adult internet users in the world. So now I'm going to go ahead and find my standard deviation. My standard deviation here is going to be based on the square root of 0.75 times 0.25 divided by 1,000. So this is the standard deviation of my sampling distribution, and I'm going to be basing that on the sample size that I'm taking. So I go ahead, I just plug this into my calculator. So you take the second square root, 0.75 times 0.25, you divide it by 1,000, and you get that square root, and I'm going to find that my standard deviation here is 0.0137. So this is a percentage. I'm saying that our mean or our average distribution is 0.75%. So when we do the 75% of respondents on average are going to say that they've watched a video or they watch online videos, and that's going to vary by 1.37%. That's going to be your typical variance that we see. Now, is the sampling distribution approximately normal? So we're going to do NP, or the number times the proportion, which in our case is 0.75 times 1,000, which is equal to 750. We are going to do 1 minus P times that N, that sample size, that's 0.25 times 1,000. This is 250. So we've got both of these. So we have N times P and N times 1 minus P, or our sample size times our proportion and our sample size times 1 minus our proportion, are both greater than or equal to 10. Our large conditions is met. Since our large conditions is met, we're going to say that the sampling distribution is an approximately normal distribution. So if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution? Since all we've done is create a larger number, we can still say the large counts condition is met like very, very easily with the sample size. So this is still going to be approximately normal. This is not going to change the mean. So the mean here is going to still be 0.75. It's always going to be equal to the proportion. That does not change with sample sizes. However, our standard deviation will change here, because now, as opposed to doing this as the square root of 0.75 times 0.25 over 1,000, we're going to do it over 9,000. And so you go ahead, plug that in on your calculator. And we'll find that our standard deviation here is 0.0045. And obviously this has gotten a lot smaller. So in that first condition, when we had 1,000 people, we were saying that with that mean of 0.75, we would expect the typical variance from that mean to be about 1.37%. So getting something like 74% of respondents saying that they watch videos, or even like 73, even 72, because that's still within 2 standard deviations of the mean, wouldn't be too shocking to us. We wouldn't be shocked if we had 72% of people saying, okay, we watch online videos, because it's within 2 standard deviations. Now, this 0.00456, that's cutting it down to now 2 standard deviations is still less than 1%. So even if we have a 74% response rate, we're going to be like, hold up, this is over 2 standard deviations. We're almost saying at 9,000 people, almost every single sample should come back like not exactly 0.75, but now we're getting like, we're really cutting hairs of our proportions. We're measuring our proportions with a degree of exactness which is greater than before. And we're seeing like your mean is at 0.75, and we're only going out to like 0.74, a little bit below, a little bit above 0.76 in our proportions. We're really dialing it into that mean, and that's because our sampling distribution is so big here. And the bigger your sampling distribution, the closer to that mean you're going to get. And then from here, if I wanted to do something like figure out what is that probability, so like let's work with this 9,000. If I wanted to figure out what is the probability of getting 76%, this is where I would go through the process of 0.76 minus 0.75 over that standard deviation of 0.0056. I would find my z-score. I would use that z-score to get my proportion. And then from that proportion, I could go ahead and use that z-score to get my proportion. And from that proportion, I could go through and I could basically say, like, this is the proportion of people. If I'm trying to figure out 76% or above, that's where I do, okay, this is the percent of people who would answer 76% or below. So now I can do 1 minus that to figure out what is the probability that 76% or more people watch online videos in a sample that large. Is this sample, so if I get something that's like 78, is that telling me that maybe our results are off? Things like that. Is this challenging our assumptions? So we can use our normal distributions in that way. The normal distribution rules still apply, and once you start figuring that out, we're still going to do what we did in Chapter 2 with our z-scores, with our Table A, with our figuring out our proportions, so on and so forth. All right, you guys have a homework assignment tonight. Please reach out with any questions or concerns, and have a great night.